Imagine an artificial intelligence capable of instantly solving complex puzzles, writing poetry, or even drafting legal briefs. It meticulously lays out its logic, step by precise step, like a master chess player calculating every move. You watch it work, convinced you're witnessing true understanding. Then, the final answer flashes on screen, and it's completely, bafflingly, wrong. Not a small mistake, but a fundamental error that contradicts everything it just thought. This isn't a hypothetical glitch. It's a documented reality, a paradox at the heart of even our most advanced language models. For years, we've assumed that if an AI could show its work, following a chain of thought, then its final answer would naturally be correct. It's what we expect from human intelligence. Sound reasoning leads to sound conclusions. But recent findings, specifically studying models like Claude Sonnet 4, have revealed a profound disconnect. Researchers devised tests, known as novel operator tests, to probe this very issue. What they found was astonishing. At deep levels of internal processing, the model executed perfect logical steps, exhibiting what looked like flawless reasoning, yet consistently delivered incorrect final answers. It wasn't about the AI making a simple miscalculation. It was about a fundamental dissociation between its internal, seemingly correct logic and the truth of its output. Why does this happen? Most people assume advanced AI thinks like us, building a coherent internal model of reality. But that's where everyone is wrong. Large language models are fundamentally sophisticated pattern-matching machines. They predict the next most probable word or token in a sequence. Their reasoning is often an emergent property of these predictions, not a genuine internal truth-seeking process. The chain of thought we see isn't necessarily the model thinking, but rather it generating a plausible thinking process based on patterns it's observed. It's like an actor flawlessly performing a role they don't truly understand. The incentive is to produce coherent, believable output, not necessarily to arrive at objective truth, revealing a core trade-off. This fundamental disconnect between internal process and external truth is a critical hurdle for deploying AI in sensitive domains, from legal reasoning, where a single logical error can have catastrophic consequences, to medical diagnostics. If an AI can perform perfect internal steps, but still be confidently wrong, we can't fully trust it. The critical insight here is that the problem isn't necessarily what the model processes, but how it processes and verifies its own internal state before delivering a final answer. This recognition has ignited a new frontier in AI research: how to implement self-refining feedback loops during inference, allowing the model to recalibrate its own reasoning in real time. Early attempts at self-correction were straightforward. After generating an answer, the model would be prompted, "Is this correct? Review your reasoning." It might even generate alternative answers and pick the one with the highest internal confidence score. But this often proved insufficient. The model was essentially asking itself the same question, using the same flawed internal pathways that led to the initial error. It's like asking a student who just got a math problem wrong to check their work, without giving them a new perspective or a different method. The student often repeats the same mistake because the fundamental understanding hasn't shifted. To understand true self-refinement, imagine an architect designing a skyscraper. They don't just draw the final building. They continuously consult structural engineers, review material science, run wind simulations, and revise their plans before a single brick is laid. They have internal critics and external data loops. A truly self-refining LLM aims for this depth during inference. It's not just checking its final answer. Instead, it generates internal critics or alternative viewpoints, creating multiple internal thought paths. It might reevaluate its initial premises, identify potential logical fallacies within its own thinking, and then use these self-generated critiques to actually recalibrate its internal reasoning steps, essentially revising its own blueprint for the solution, not just the final drawing. This is a profound shift from simple error checking to genuine internal metacognition. This kind of deep, internal recalibration isn't simple to achieve. It dramatically increases computational cost and inference time. Imagine the architect running dozens of simulations for every design choice. For an LLM, generating multiple internal thought paths, evaluating them with internal critics, and then using that feedback to adjust its own subsequent reasoning requires far more resources than simply predicting the next token. There's a constant tension between speed and accuracy, between efficiency and reliability. The hidden incentive for many developers is to optimize for quick, plausible responses, not necessarily for slow, perfectly reasoned ones. Crafting effective internal critics that can genuinely identify flaws in the model's own thought process, without just mirroring its existing biases, remains one of the greatest challenges. The journey from an AI that flawlessly recites logic but fails on truth to one that can genuinely interrogate and recalibrate its own reasoning is transformative. It moves beyond merely making LLMs sound intelligent to making them act intelligently and reliably. This isn't just about building bigger models or feeding them more data. It's about fundamentally changing how they internally process and verify information. As we push AI into increasingly critical applications, understanding and implementing these hidden feedback loops during inference becomes paramount. It's how we move towards genuinely trustworthy AI, an intelligence that doesn't just mimic thought, but truly learns to think and, crucially, to correct itself.